Okay, so what do I have today? I have Modern Quantum Mechanics by Sakurai and Napolitano. This is the international edition. I'm not supposed to have this, but the American edition was hardbound, and I hate hardbound ones. So yes, it's cheaper, but it's also softbound. So I prefer softbound books generally. So I got this guy. This was not the book I used for quantum mechanics. I do not have my graduate text here. My graduate text must be at work. That was Koen Danuji. I have a book by Koen Danuji here, but actually I have a couple books by Koen Danuji here, but not that one. This is my book. That I use quite a lot. You can see A Modern Approach to Quantum Mechanics by Townsend, or International Series in Applied Physics. This is what I used in as an undergraduate, and actually I used that a lot instead of Koen Tanuji in my quantum mechanics class in graduate school. When I looked at a review of this one, I looked at a review of Townsend, probably the second edition. This is the first edition. Someone was complaining about, basically it was Sakurai, the same approach as Sakurai. And I don't know why that's a complaint. In general, like we said before, a lot of books you have this, medieval monastic mimicry or something like that was somebody said about textbooks. But Townsend's a little lower a level than Sakurai. I think Sakurai is a graduate text. And the thing about them, though, is that they start out very, very well. They start out with the Stern-Gerlach experiment. And somewhere around here we have a video for the Stern-Gerlach experiment. So over here with Townsend, you have the Stern-Gerlach experiment, and you're just using this to introduce the ideas of quantum mechanics. Again, Sakurai has the same sort of thing. You're looking at a lot of the basic ideas of quantum mechanics with the Stern-Gerlach experiment rather than starting with what you get over here, which is the Schrodinger equation. So you're starting off, here we go, just with a sort of Stern-Gerlach experiment. I mean, for Townsend, it's basically the first chapter, right? That's an undergraduate text. For this, it's actually just the first section. And you're talking about what's happening to the spin angular momentum when you are doing this fairly simple experiment, and you're looking at some of the strange things that happen. And if you look at the video I put up before the Stern-Gerlach experiment, I talk a lot about that. And I think that's a really good way to start. So when I saw that review of Townsend saying that basically this approach by Sakurai was the same approach, but I figured out that this was a graduate text. I picked up a copy of this, again, a cheap one, and then I actually worked it. I should have brought those from work too. I actually worked through the textbook a couple of summers ago, just for fun, right? That's what summer is for fun things like working through graduate textbooks. And so, I had a good time going through this. It had some fun things in it. And I think I just saw one, right? So, this is neutrino oscillations and, differences between the mass eigenstates. There's something else in here about gravitation and quantum mechanics showing that there is an interaction there. I mean, it's a very good textbook going through a lot of different things. I think this is a little more applied. Sakurai has another one. I think this is a little more applied than that one. So, I mean, it is just a graduate level, or it's just a textbook. It has the normal things. It's mostly just regular old textbook material. So, like I said before, it starts off with that Stern-Gerlach experiment, just to give you an idea about what quantum mechanics is all about. Then it goes through bras and kets and all those sorts of things. Bras and kets are state vectors. But a lot of times when we're going to talk about these, we're talking about base vectors, right? Base kets. And we talk about matrix representation. It's also very important. But when we're looking at the basis things, these are what are generally going to be the results of our observations. That's what we care about there. That's how we want to set up, generally, that's how we want to set up our spaces in quantum mechanics. Then we talk about what measurements are, observables, and uncertainty relations, and all those sorts of things that are just basic stuff, right? This is the fundamental concepts. These are fundamental concepts. How to do changes of basis, position, momentum, and translation, and the wave function in position and in momentum space. So you have to change the wave functions from time to time to get different sorts of results. You just have to be able to do that. Then we get into quantum dynamics, and you end up with your Schrodinger equation, all those fun things. Talks about differences between Schrodinger's and Heisenberg's pictures. What is evolving? Is it the wave function or is it the operator? Go into our simple harmonic oscillator. That's one of our favorites. It's the physicist's favorite thing. So when you're doing that, if you haven't taken physics 1, when you're looking at physics 1, really, really care about that simple harmonic oscillator when they introduce it to you, because that's our thing, right? I have a hard time explaining that to our students. Schrodinger's wave equation. Basically, we get a wave equation. The Schrodinger equation is the wave equation. And it is a wave equation, excuse me. Then we have propagators and finite path integrals. Doesn't really do a lot with that. This is really going to go into other things. And then we have potentials and gauge transformations. All right, then we go into the theory of angular momentum. This is the thing that everybody hates. Okay. Now, we're talking about just this Stern-Gerlach experiment. We're talking about it sort of the way Townsend looks at it. It's very nice. It's very easy. It was something that I wanted when I was teaching modern physics to use rather than, sort of canned expressions for the Schrodinger equation, because those canned expressions don't really teach you anything, right? Whereas if you have a very simplified system like in the Stern-Gerlach experiment, then the spin angular momentum is very easy to work with. When you get into all these other things over here, when you get into rotations and other sorts of systems, the full theory of angular momentum, then life starts getting kind of difficult. You have to worry about orbital angular momentum as well as the spin angular momentum, and starting to deal with central potentials, and it's just getting pretty bad, right? And it's just a lot of math, right? At some point, this is the place where if you're going to get overwhelmed in math, this is where you're going to get overwhelmed in math. Maybe a little bit in approximation methods. But I didn't really find those to be too bad. The approximation methods, like down here in chapter 5, these things are okay, right? There is a lot of math, but the math is not so horrible, right? You could just, you're looking at perturbation theory or something like that. All you're doing is you're sort of finding a simpler answer and then saying, okay, I'm going to use that simpler answer to help me find a harder answer, right? A more detailed answer. So I'm looking for a simplified system, and then I go off to something a little more complicated. With the angular momentum, that's not really the case. When you're dealing with those spherical harmonics, that's probably the only place where in a normal quantum mechanics class your ears are going to start to bleed. Assuming that you get to this graduate quantum mechanics class, those aren't going to be too horrible. He does have some symmetry in quantum mechanics. That's good. lattice translation, saying that, this is going to be something that's really good for condensed matter physics. Maybe I should talk about some statistical physics stuff. They're just farther away from my desk, so it's harder to grab them. Let's see. But I did a lot of stuff in statistical physics. It's pretty fun. Then we get into scattering theory, and we have, our Born approximation and all these other fun things that you'll remember. I wish I could remember how to pronounce iconal approximation. That's really important, actually. It's not so important here, but as I probably talked about Sleeping Beauties and theoretical physics before, that this gets really important if you're trying to understand what happens in the long run. So scattering is essential. But in general, I think it gets short shrift in your mechanics class. So it's complicated, especially in mechanics, especially if you're using like an inverse square potential or something like that. If you're trying to do the integrals, if you're trying to analyze it with the Hamiltonian or something like that, it's a little bit annoying, right? It's a big chunk of math. And so even though this isn't so bad, even though in quantum mechanics it's not as bad as in classical mechanics, my feeling, I guess that's just my feeling, but it's not as bad in quantum mechanics in my experience as in classical mechanics, the math. If you haven't gotten through that math for the classical mechanics for shooting a ball at or not shooting a ball, the ball is actually fairly simple, right? If you're shooting a ball at a large object like this, right, and it's bouncing off, and you're looking at that scattering, that's not too bad. But if it's that inverse square, and your ball never actually touches, right? If it never actually touches the thing and doesn't physically hit it, the actual expression is a little hard to work through the first 5 or 10 times. Resonance scattering, again, this is going to be really, really important, especially if you're doing anything in condensed matter physics. Then identical particles. Man, you need to know about identical particles and electrons and things like that. This is Pauli exclusion principle, but it's also coming back to, the statistical physics stuff. When you get into statistical physics after this, you have different distribution functions based on different kinds of things for your identical particles. If you have fermions, if you have bosons and stuff like that, it becomes extremely important to understand what identical particles mean for different things. So going through something like this and looking at stuff like that, looking at what identical particles mean is important. And then with the quantization of the electromagnetic field and relativistic quantum mechanics here, basically you're getting into a brief introduction to quantum field theory. You're ending with that brief introduction to quantum field theory, which is very important. Actually talking about this, right, makes me think that the reviewer of Townsend was a little bit was exaggerating when he said that this book was exactly like Townsend. Not just because of the graduate level and stuff like that, but, I went through Townsend, I went through this book, and although, when I went through this book, it took me a summer. When I went through this book 15, 20 years earlier, yeah, 20 years earlier. Is it only 20 years earlier? It was maybe 25. Yeah, it's 20 years earlier. It took me 4 months, right, because I was taking a class. So it's, even when I was taking this, even when I was working through this, I wasn't really comparing it along the way. But now when I'm talking about this and comparing them in my head, there is a significant difference between what's going on in the books. One, this is obviously a lot more complicated, but two, in the style of presentation and so forth. I think they're pretty good. Now, I think Napolitano's work here in translating Sakurai was really quite good, and he added some things in here. If I remember from reading the preface, he added a bunch of stuff in here, and I didn't see it. So somewhere in here there is somewhere in here there's the graph that I was thinking of, and I'm not finding it, so we'll ignore it. This is just a textbook, so it has some interesting things. Like I said, it has that discussion about gravitational oscillations due to the gravitational effect. That's pretty important. It's important less because of what it means for quantum mechanics in general, but more because of the kinds of myths we sort of tell about quantum mechanics and gravity. Quantum mechanics and gravity go together perfectly well, right? You can do quantum mechanics and gravity as long as the gravity is weak. Very well. I mean, you just use the gravitational potential and you're done, right? I mean, it works perfectly. You don't have to worry about that. It's just that the myths are a little, it's just that when you get to the really, really complicated things, it gets harder and harder, and there's a point where quantum mechanics and gravity don't quite work, and that's actually at in a very, don't quite work together, and that's actually very much in a very small size or highly dense regime where you have to worry about quantum mechanical effects at more or less the Planck scale, at these really tiny scales. We do have a recent podcast about quantum effects in gravitational wave astronomy, so you might want to look at that because people are trying to figure that out now. We've got LIGO and some other experiments, and people are looking at that. And actually, I was listening to Carlo Rovelli also talking about that as well. He was not one of the people we were talking about in that podcast. Now, you see, these are standard sort of physics questions, right? This one is just using these creation and annihilation operators, evaluate certain things. Over here we have, sort of an exploratory problem. Maybe it's a little bit scaffolded, maybe not. Here's my favorite. You define something in the problem, so it's not something that you see back here in your wonderful text about what we're doing. We give you this idea, this correlation function, and then we say, okay, now we've got this correlation function. You're going to, this is pretty much it, do something with it for a particular thing. So all of the learning about the correlation function has to happen in your thinking about it. Usually it's something that's fairly simple, something you should be able to do. Here are some, put particles in a box sort of deals, one-dimensional trapped atoms, very, very, very simple things. Things that if you've done these things before, you know all about, right? So you probably, so this is a particle in a box. This is particle on one side, infinite barrier on the other. If you've done quantum mechanics, you've done those before. And, problems are always more or less the same. Okay. So, or the same kind of problems. Different books will have different problems and things like that. I didn't see any problems in here. I didn't think the problems were extra hard or extra easy or remarkable in any other way, to be honest. But I mean, they were worth working through, considering I hadn't had a quantum mechanics class at this level for about 15 years when I did it, maybe a little more. Okay, so yeah, I mean that's that. I shouldn't think too much about what I did when. That's not what I'm going here. So I said I like this book. I think this is a pretty good book. I worked through it on my own, so I think other people can too. That's a very, very good recommendation. I'll say that. That's not true for Koen Tanuji. I don't think you can work through Koen Tanuji on your own. I think you need somebody to help guide you through it. Or, like I did, you can use your undergraduate quantum mechanics text to help guide you through Koen Tanuji, because that's a lot of stuff. Actually, Messiah is too. I think Messiah you can get in a Dover edition, so but that's still a huge book. Anyways, thank you very much for listening to this, and I will come at you with something else next week, whatever I think would be fun to talk about. Bye now.